Hi, in this tutorial we have an exercise related to stereoisomers. The question in the exercise is identify the relationship in each of the following pairs of molecules as enantiomer, diastereomer, constitutional isomer, or unrelated. Assign R as cis-trans or easy if the pairs are stereoisomers of each other. Let's look at the first option. In the first option, we have two different types of representation. The first one, we call it sawhorse representation, and the second one is called Fisher projection. Let's look at how a sawhorse representation can be. In order to do that, we need to use a real model, and I'm going to bring here the real molecular model of the first molecule and how it looks in 3D. So in sawhorse representations, two bonds like carbon and carbon, this carboxylic acid's carbon and this chiral center's carbon is parallel to the plane of screen. And also we have another chiral center here, and the chiral carbon and the methyl carbon bond is also parallel to the screen, plane of screen. And the molecule is held a little bit oblique like this. And so we can see also the carbon-carbon bond between two chiral center, and it is as if receding inside the screen plane. And we can see that in the front chiral center, hydrogen and bromine, these two groups, are coming out of the plane. And at the back chiral center, hydrogen and bromine are going inside the plane, screen plane. It's something like this if we hold. So this is how we can visualize a sawhorse representation on a 3D model. So now, how are we going to determine the stereochemistry of each chiral centers, whether they are R or S stereoisomers? So let's write here the same model with a big version, and we can assign R or S configuration following Van Ingold-Preluk sequence rule. So I'm going to here write a bigger version. So these two are parallel bonds, and these two are chiral centers. And we know that the front chiral carbons groups, hydrogen and bromine, should be represented with wedge bonds because they are coming out of the plane, this part. And the back chiral carbons, hydrogen and bromine, should be drawn with the wedge dash bonds because they are going inside the screen or paper plane. So let's write, this is bromine and hydrogen. This one is carboxylic acid. This one is methyl. This one is hydrogen and bromine. Now we can clearly see the two chiral centers and the relative 3D arrangements of the groups around the chiral centers. I'm going to use a red color to indicate the front chiral carbon, and I'm going to assign priorities based on Hahn-Ingold-Preluk sequence rule. And we know that hydrogen has the least atomic number connected to chiral carbon, so it should be ranked number 4. Bromine has the highest atomic number. Then the carbon, this carbon should be ranked as number 2, and methyl carbon should be ranked as number 3. If we do 1, 2, 3 clockwise or counterclockwise rotation, so it's from 1 to 2, 2 to 3, so the rotation is counterclockwise, and we normally say this is an S configuration. If the hydrogen is going inside the plane, paper plane or screen plane, but it's opposite. So instead of saying S, so we have to say this configuration is R. Now we can do the same for the back chiral carbon, and I'm going to use green color to indicate this chiral carbon. And we know that hydrogen should be number 4 based on the sequence rule. Bromine should be number 1, and this chiral carbon should be number 2, and the carboxylic acid carbon should be actually opposite. This should be carboxylic acid should have higher priority, so it should be number 2 because it's connected to oxygens, double bonded and single bonded oxygen, so it should have high priority, and this chiral carbon should be number 3. So now let's look at the rotation from 1 to 3. So 1, 2, and 2 to 3. So this is counterclockwise rotation, and it should be designated as S, and hydrogen, the number 4, is receding into the plane, meaning going inside the plane. It's shown with the dash representation. It's really an S configuration. So let's write here, the top carbon should be S, the bottom carbon should have R configuration. Now let's come to the second molecule. And second molecule, so let's say this is a sawhorse representation. And the second one is Fisher projection. Okay, how is a Fisher projection? Basically, I'm going to again use a molecular model to show you how it can be. So I will show you symbols. And this is exactly how this molecule looks in 3D. So here, as you can see, we have a carbon-carbon bond between two chiral centers, and bromine and hydrogen on the upper carbon. They are coming out of the screen plane or paper plane, and the methyl group is going inside the plane of the screen, and at the bottom chiral center, which is this one, we have hydrogen and bromine again coming out of the plane, and we have carboxylic acid going into the plane. So I'll hold a little bit like that. You can easily see. This is kind of an eclipse conformation, but this is how this Fisher projection should be on a real 3D model. So we know that this right and left bromine hydrogens, they are coming out of the plane. Top and bottom methyl carboxylic acid groups are going inside the plane. So how can we draw this one with the dash and wedge representations? Let's here do it. So as we say that, let's use the black color again. As we said that this chiral centers should be drawn as a straight bond, and I'm going to make it a little bit bigger. So here, this bromine and hydrogen, they should be represented with wedge bonds. So bromine and hydrogen. Also for the bottom part, it should be the same. So this is hydrogen and bromine. The top one should be methyl and the bottom one should be carboxylic acid. Again, we have to follow the same. So I'm going to use again red color for the same chiral carbon. So the one with the methyl, so this one, this is the chiral center, and we know that hydrogen should be number 4, bromine should be number 1, this carbon should be number 2, methyl should be numbered as 3. So, and hydrogen is coming out of the plane. You have to keep in mind. So let's look at from 1 to 2, 2 to 3. So the rotation is counterclockwise. So I'm tempted to say it's S, but it should be the opposite because hydrogen is coming out of the plane. So it's going to be R. Let's come to the second chiral center. Let's mark with an asterisk. Then we know that hydrogen number 4, bromine number 1, carboxylic acid's carbon should be number 2, and this carbon should be number 3. So let's look at now what is the rotation of groups 1 to 2, 2 to 3. So this is a clockwise rotation. Again, we can say this is R, but it should be the opposite because hydrogen, again, it's coming out of the plane, so it's going to be S. So again, let's mark it here. The carboxylic acid's carbon, it's S, so this is S, and the methyl one, the chiral center attached with the methyl one is R. Let's look at here. Here R and here R, and S configuration is S configuration. So basically the same carbons have the same configuration. So for that reason, we are going to say that these two are identical. Let's write it here. They are identical. Now let's move to the second option. The second option, our job is a little bit easier because if you check the first molecule of the first option and the second option's first molecule, they are same actually. So whatever this is, so it's going to be the same. So let's write it here. So this is SR. Okay, yeah, based on this one. If you look at the second molecule, and we can see that there's a mirror plane between these two molecules, and they are reflection of each other. That's the first thing we can observe. Or, for example, if you look at the hydrogen and bromine on this molecule, and on the other side, they switch the locations. So meaning that if you switch locations of two substituents on a chiral carbon and keeping other two substituents stationary on the same positions, locations, you end up with an inversion or the enantiomeric part of that mark. So if this is S, this should be R. And let's look at the second part. Again, hydrogen and bromine exchange the places. So if the first chiral, the chiral carbon on the first molecule is R, it should be S on the other side. So they are mirror image of each other. When they are mirror image of each other, and if they are not superimposable, if you have two chiral center, so we say that these are enantiomers of each other. They are enantiomers. Okay, let's move to the third option. In the third option, we have a chair cyclohexane. This is the first position, and this is the fourth position. 1 iodo 4 third butyl cyclohexane. And we can see that if we have two substituents on a ring, on a cyclic structure, we can have these trans isomerisms, or they can be on the same side of the ring or on the opposite face of the ring. But let's check structure. When we look at the structure 1,4, 1,4 substitute cyclohexanes, they have a symmetry plane. It's not very visible from this drawing, but if I draw a different version of skeletal structure of cyclohexane, let's say this is the iodine and this is the T-butyl, you can observe that there's a symmetry plane of symmetry cutting the molecule into two halves. Okay, it's again very useful if you use a molecular model. I'm going to bring it here, a molecular model of 1-iodo 4-terbityl cyclohexane. There are too many hydrogens. It may not be very visible, but if I hide the hydrogens in the model, you can see that this part is a cyclohexane chair conformation, these 6 carbons here, and this part is third butyl group. This is the iodine part. So if I rotate the cyclohexane like this, you can clearly see that we can cut the molecule into 2 equal halves, meaning that there's a plane of symmetry passing through this plane, meaning that so basically these 1 and 4 carbons are not chiral centers, because if you just like add, I'm going to add here it here hydrogens. Okay, there is a hydrogen here, which is an axial one. There is another axial hydrogen here. So we have 2 different groups connected to this carbon, but this part and this part same. So basically we don't have 4 different groups attached to this center. But the same holds true for the first carbon. Okay, but what is the relationship between them? There is an isomeric relationship. So just let's clean the structure. Okay, so again, like I'm going to put here axial up hydrogen, and the equatorial iodine is facing downward, and this is facing the axial hydrogen upward. Here, the equatorial third butyl group facing up, and the axial hydrogen facing down. So this is up, and the iodine is down. So basically, they are facing opposite. So this is the trans isomer. And let's come to the second molecule. I have an equatorial hydrogen, which is facing downward of the ring plane, and I have iodine facing upward. Here again, an axial down hydrogen and an up T-butyl group. So T-butyl and iodine are facing the same side, the same face of the ring. So this is the cis isomer. So what is the relationship between this one and this one? It is cis trans isomerism. What kind of isomerism is this? This is, we can call they are diastereomers also, because they are not, they are isomers, stereoisomers, but they are not they are not superimposable also, and we call them diastereomers. Okay, let's come to the option D. In option D, let's here clear some space. Okay, we have here an alkene. As you know, like alkenes can have easy or cis-trans isomerism. And also we have here a bicyclostructure. And when you have bicyclostructure, you may have a special type of cis-trans isomerisms. What is this isomerisms actually? Let's analyze it. Here we have a bicyclosystem which have 2 carbon here, 2 carbon here, and 2 bridge carbons. And also in the bridge we have 1 carbon. So 2 bridge had 1 bridge carbon, and 2 carbon in the 2 different rings. So this is like 2 to 1 bicyclo. how many carbons we have? 7, right? Heptane, cycloheptane, bicycloheptane. The same is for this one. When you look at the position of or the orientation of the bridgehead, it's facing upward, and also the same here, facing upward. And here we have an alkene functionality, and in this alkene we have a methyl substituent, and it's facing downward, and opposite of the bridge has the bridge carbon. The bridge carbon is pointing upward, and this methyl on the double bond facing downward. If we check the other one, the bridge carbon and the methyl, they are facing the same direction. So basically, they are not same. They are isomers. They are stereoisomers. They are not mirror image of each other. So we can say that like they are cis trans. So this will be the methyl and the bridge are on the same side. So we can call this one as a cis on the same side. This is the trans, and they are diastereomers. Let's come to the last option. In the last option, I think it's easier to see the relationship here. If you place a mirror here, they are a reflection of each other. So that's the first thing. The second thing, are these molecules are same actually? Uh, how can we understand? If you rotate this molecule 180 degree, and what's going to happen? You can place everything on top of each other. So they are superimposable. So meaning that these two molecules are identical. Thank you so much for watching the video.